Hi everybody, this is a continuation of our video on two-dimensional collisions for momentum and impulse. So make sure that you've seen part one of the video before watching this segment. So where we left off in part one was we analyzed the situation only in the x direction and only in the y direction. So we created individual momentum impulse bar charts for each, and we come up with an equation from each bar chart. So when we think about the initial problem, I'm going to draw this down here. A straight line would be great here. When we think about the initial problem, we have one vehicle approaching the intersection, so it's moving east. We have a second vehicle approaching the intersection moving north, and unfortunately we said that these two collide together and end up with a final velocity that is the same. So they're stuck together. There's some type of inelastic collision here. And we know that if this is v final, that we could break that vector down into its x component and its y component. And this little angle here, the angle between v final and the x-axis, we can call theta here. And this is an angle that's important to us. It'll help us describe the direction of v final. So that's really what our goal is, to find that. So just as a refresher here, vx, so velocity, this x component of the velocity, is v final times the cosine of theta, and vy is equal to v final times the sine of theta. And we've seen this pattern previously when we've resolved forces, we've resolved velocities, things like this. So now we're doing this for momentum, for the purposes of momentum. So when we think about our x analysis, we know that any of these momentum values is really the mass. In this case, the subscript p tells us the mass of the pickup truck times the velocity initial of the pickup truck. Here we're going to have mass of the car times v final of the car in the x direction. And the v final of the car in the x direction is v final cosine theta. And this one will be mass of the pickup truck times v final cosine theta. Now we know the mass of the pickup truck because it was given in the problem. So this is our 1,600 kilograms. The initial velocity was also given. That was 20 meters per second. Mass of our car is given. Okay, and again we still have these variables for vf cosine theta. And again, the mass of that pickup was already given, so I'm going to copy this down. I'm running out of room here, so I'm going to just put our VF cosine theta, but it's still just being multiplied. All right, so 1,600 times 20 gives us 32,000. And this VF cosine theta, it's a like term, it's the same variable here. So the combined mass is 2,900 kilograms, and we can multiply this by VF cosine theta. Ultimately, I'd really like to get VF by itself, so I'm just going to divide out this mass number of 2,900 and the cosine of theta. So you can see that these will cancel, but I need to make sure that I do this to the other side of the equation. All right, and I end up with VF equal to, I'm sorry about that, 32,000 kilogram times meter per second. I'm just going to leave this exactly how it is, 2,900 kilograms times the cosine of theta. Alright, so now let's do the same type of work with the y analysis here. So again, any of these momentum values is just the mass times the velocity. So here we're going to have the mass of the pickup truck, I'm sorry, the mass of the car, that subscript C is car, which is 1,300 kilograms, times velocity initial of the car, and that was given to be 16. So I'm just going to put that right in here, equal to mass of our car times, this is going to be, because this is the y analysis, the y component of this final velocity. So this is going to be v final sine theta plus mass of the pickup truck, which is 1,600 kilograms, times v final sine theta. And I end up on the left side here with 20,800 kilogram times meter per second equals 2,900 kilograms times VF sine theta. Alright, so now we're getting somewhere here. I noticed that I have two variables. I do have VF and I do have theta in both of these equations. However, VF shows up in the y analysis and it's showing up here in the x analysis. So what I'd like to do is I'm going to plug in what I know V final is equal to in terms of theta so that I can basically eliminate this V final variable right over here. So in order to do that, I'm going to have to make a little bit of room here, so I cleared out our diagram. Okay, so what I have here, I'm just going to copy what I have for this y analysis over here. I just want to give myself a little more space. I have 20,800 kg times meter per second is equal to 2,900 kilograms times, here's that V final, and I'm just going to sub in what I know V final to be, which is 32. Let me erase that. I just don't want to use up too much space here, guys. Alright, so this is times 32,000 kilogram times meter per second, all divided by 2,900 kilograms times the cosine of theta. And don't forget about multiplying it by this sine of theta up here, so times sine theta. First thing that I notice is that this 2,900 kilograms and this 2,900 kilograms will divide out. They'll cancel out. So this is going to leave me with 20,800 kilogram times meter per second is equal to 32,000 kilogram times meter per second times sine of theta divided by cosine theta. And I would really love to get sine of theta divided by cosine theta. So if I divide both sides by the 32,000, I could end up, so let me divide this by 32,000 kg times meter per second, and I'm going to divide this whole side as well by this 32,000. When I do that, what's interesting is these units completely cancel as well. And when I divide out the numbers, I get 0.65, again, no units, is equal to the sine of theta divided by the cosine of theta. And I know that the sine of theta divided by the cosine of theta is the same thing as the tangent of theta. So I know that the tangent of this theta, some angle, is equal to 0.65. Really, I want to find theta. So I'm going to use the inverse tangent function here to give me theta. And when I do that, I find out that this angle is equal to 33 degrees. And this is extremely helpful for us because it's basically telling us, remember that V final angle, once these two cars collide, this V final, it's telling us that the angle between V final and our x-axis is 33. And if this is the case, if we know this 33 degrees, then we could use it here, or we could use it here to then produce this V final value. So let's give that a try. If I put 33 degrees in instead of theta, so if I put 33 degrees instead of theta, so we do 32,000 divided by 2,900 times the cosine of 33 degrees, I get V final here to equal about 13 meters per second. Now you can do a check for yourself, and you could also throw in this 33 value over here and solve for VF, and if you did that, you'd also get this 13 meters per second. So it's been a long way. It's been a long road to here, but you have now found your answer. You found not only is V final equal to 13 meters per second at an angle of 33 degrees north of east. Okay, this is the final velocity vector of these cars involved in the collision, but you also have your x components, your y component. There's so many values that you've really been through to get here. But again, the big idea was always separating your x analysis from your y analysis. Let me know if you have any questions. It's a pretty complex topic, but I know you can do it.